So this is about error correcting code. Unit 8 is about error correcting codes, which is, like in the compression chapter, encoding some source text to some coded text, but here in a way that makes it possible to recover from errors in the transmission. All right. This will be a fairly short unit compared to the compression and text indexing ones before. I'll talk a little bit about where this arises and where it comes from, and also the context in terms of human communication. And then we'll get mathematical, and we'll talk a little bit about lower bounds, about what's the best possible way to do certain things. And then I'll talk about one specific code, or really two codes, that help correct or detect errors in this context. Okay. First of all, most communication by definition is noisy, in the sense that communication always involves two parties. There's one person speaking, another person listening, for fairly liberal definitions of what listening and speaking means. And it usually involves mistakes. It involves noisy channels. Noise can be in the acoustic sense, because your neighbor mows the lawn. It can also be that the sender makes non-perfect transmissions, or it can be that the language itself is not unique in its meaning. The semantics of natural language is not always well defined or not always formal. And then, well, we don't all speak the same languages. That makes the whole problem even more challenging. So how do we humans cope with this range of issues? One thing that most of us automatically do is slow down or speak up, so that we better balance the noise signal to noise ratio. We slow down to make it easier for others to filter out noise. We speak up to make our voice outsound the noise. And ultimately, if someone tries to tell you something and you can't possibly figure out what he said, you will just ask that person to repeat what they said. Interestingly, humans are quite good at decoding messages written in natural language text, even in the presence of errors and noise. So I put down this sentence here for you, but I'd actually like to make this a question on Pingo. So let's head over there. Same mistake as last time. Now I created a new window. I'd like to give you 2 minutes just to tell me how easy or how hard it is for you to read this little scrambled text. Just as a little experiment to see how well this joke or this comparison here works. It's possible we don't need the full 2 minutes for this, but I'll give you a little bit more time. Let's test this. If you're done, then write me in the live chat that you're done. Maybe this is an effective way to use the live chat. Okay, thanks Ben, at least for one it worked. Okay, a couple of people, but there's a couple more connected, so I'll wait a bit more. The interesting thing about this, deciphering this text, is of course it depends a lot on your language background. If you're a native English speaker, it will be easier. If you've spent a lot of time in English-speaking countries will be easier. If you're just recently getting used to speaking English or reading English, then it's definitely harder to do. All right. Okay. At least one person said they can't actually figure out what that means. That's interesting. Most people seem to have no problem at all to read this. Whereas if you look at this text in more detail, what's actually written there is pretty much gibberish. There's hardly any word that's correct except for it and a few. I left the redundancy correct because I wanted to stress that point. But it's really interesting how much redundancy is built into natural language. You can, in particular, swapping two characters around seems to not at all interfere with our ability to read the word. And that has to do with how humans read, how our eyes and our brain breaks the words into blocks. It's much more important that the extensions above and below the main lines are preserved than the actual characters, it's all pretty interesting, but not really the topic of this class. So thanks for taking part in this experiment. On the more abstract and mathematical side, I would say there's two things we need to separate. And the one thing is to detect errors. Detecting that something has gone wrong in this sentence is easy for us. We easily recognize, well, pi might be a word. This I don't even know how to pronounce it, so it's obviously not an English language, a word in the English language. And I can't possibly figure out what that means, but I definitely can say something went wrong when you translated, when you transmitted that sentence. The other option is detecting errors is fine, but we might also want to correct them without asking the person to repeat. And here's again a sentence. I hope this one works even for the person who said they can't figure out what that sentence means. Here it's only a few isolated characters that I dropped or misspelled some words, even in somewhat common ways of misspelling them. So we don't even notice necessarily that there's a mistake here. These are two separate things, detecting errors and correcting them. And both is interesting also in a computer context. Misunderstanding what communication is all about is obviously something that's very widespread. I won't comment on the comic more than necessary, but I could spend a lot more time on lamenting on communication and the noisiness of communication. But let's instead of that look more at computerized communication. And again, here in the picture you can already see where some of the noise in computerized communication might come from. Still, much of our electronic communication is electrons traveling through copper cables, and I could imagine there's electromagnetic interference from the fan of this AC to one of those many cables. Well, maybe these are just supplying electricity and are not used for communication. But for the general concept, there's lots of ways how you get interference in communication. And this is also indicative of the type of errors that we will look at. The main point, the main type of mistake that happens in the communication that we will be concerned with in this unit is that a single bit can flip from 0 to 1 or from 1 to 0. It's not as likely in this type of setup that the code gets completely out of sync, meaning that we see more characters or less than were transmitted. because usually these cables have a fixed speed, so they send data at a fixed rate, and making time out of sync is less likely than transforming the signal in between for a certain amount of time. So we will model this as the channel is some black box in the middle, and then there's a sender on one side that puts something into the channel, and then there's a receiver at the other side. And what travels through the channels is just a bit stream, or a string of bits. So there's little zeros and ones that go through this channel, and once in a while it flips a bit and replaces it with the opposite. That's the model, that's the way to think about this. And then the goal for this unit is try to invent encodings, codes that can allow a sender and a receiver to reliably communicate through this channel, even in the presence of these types of errors. And we will be interested in if that is possible, how well it is possible, and at what cost. Again, there's two different types of robust measures of robustness. We can look at detecting errors and correcting errors. So detecting errors is enough if retransmitting a message is cheap, in particular in an internet setup where you're talking about two computers that are connected. It's easy to have bidirectional communication, so it's easy for the receiver to tell the sender, hold on, I missed package number so-and-so, could you just send that again? In that case, we can go for error detection, which usually is cheaper. But there's also use cases for error detection where we can avoid retransmitting. And that's obviously something you want to do if the communication is one way, if there's not at all any chance for the receiver to go back to the sender and say, please repeat that part. But it might also be just very costly to do so. And then we also want to avoid that. One thing that is clear is there's no free lunch like we've had for compression. We can't get these things without investing something. And in this case, we will have to add redundancy to the messages that we send. So, well, I'll draw the full picture on the next slide where it's more appropriate. But we'll be sending more bits than the actual plain message. So I'm supposing that the sender has just a string of bits that he wants to transmit to the receiver, and we don't know anything specific about this message. That could be arbitrary bits, and our method should work regardless of what the content of this message is. If that's the setup, we will have to add extra bits to this message to make it possible to detect and correct errors. We'll come back to that and make it more precise what I mean by this. If you like, that's somehow the opposite of compression. That's why I split this into a separate unit. For compression, we were trying to send as little as possible without making it impossible to recover the original source text. Now, recovering the source text should be possible in the presence of errors, and that makes it necessary to transmit more than the original source text. So in some sense, the two are complementary, but it's often a smart thing to first compress a message before you transmit it, and then apply an error correcting code on top of that. So it's not that the two act in opposite directions. They can be combined, but the goal of the encodings is clearly different here. Before we move on, I'd like you to just think about this question. I will pose the same question again after we covered some of the solutions, but just without knowing how to solve this, think about this scenario. You transmit a certain amount of bits from a sender to a receiver, and you'd like to be able to detect whether a single bit in this message has been flipped. What I mean by this is if there's more than a single error, I don't care if you can detect it. All right, so suppose there's only a single bit that got twisted. How many extra bits as a percentage of the message length do you have to add to make up for that? So let me start that question. I don't know, maybe we don't need 2 minutes because I've already been talking for one. So that's the right one. Again, if you're done, if you submitted your answer, you can post in the live chat that you're done. And maybe make this a little more fun. Try to count. So the first one who's done sends a 1, the second sends a 2, etc. That's an interesting experiment in concurrency to see how fast the stuff is. So try to send numbers. When you're done, you feel, number 1's gone. So let's see if we get nice numbers. Okay, it's slow enough for now to work, as far as it seems. All right, I think the timing's already over. Yeah. So let me rather show the table. So I don't want to really discuss the result. What I want to show is that there's a vast range of different answers, going from 1% to 100% and a lot of stuff in between. Oh, it's not sorted, so this is maybe the histogram is actually more useful. I guess by putting the 100 into the question, I primed you to answer 100. But of course, I hope you didn't let yourself influence too much by this. Okay, as I said, not a lot of comments on this. Let's do the same question, but now think about, you don't just want to find whether or not such an error occurred, but you also want to correct it. So same setup, same question, same game, but now we want to be able to correct the error as well. I would say let's do the same fun game again. That was cool. This time using letters. If you're the first, send an A. If you're the second, send a B, etc. Your instructor is a little bored while he's waiting for your answers. So let's spice this up a bit. Okay, we have 2 answers. I'm a little disappointed. I was expecting more simultaneous answers and duplicates in this game. It's good that this is not a course on concurrent programming. Otherwise, my experiment would have failed now to show you how concurrent actions can cause inconsistencies. So people are still thinking about this apparently. So I'll give you some more seconds. We have a C. All right, more answers coming in. 4, 3, 2, 1, go. All right, cool. So I like the histogram much better. It's interesting that you pick roughly the same range. Okay, now I do want to see the actual. Okay, there's a couple of people who said 100 again. What's interesting is that no one said 500 or 10,000 or whatever, a number bigger than 100. It's not a priori clear whether 100 is enough, right? Okay, so vastly different error answers again. And just briefly go back to that. Was there a very big difference between the two? I would say not that much. It's a little annoying that he flips back too. The histograms look fairly similar. Okay, let's continue with that. Before I'll talk about actual codes, I think it's insightful for this topic to think about the mathematical model for this, and also about the impossibility results. What is the best possible and what is definitely not possible. And this is what this section 2 will be about. So let's try to be a little more concrete with the model, what we do. And I'll draw the picture again. So we have our sender on one side. Then there's this channel in the middle. And what the sender puts into the channel is a string S, which is just a bit string. And the receiver on the other side gets some coded text out of this, which is C. Now, S and C might not be this is not only the channel can change the message, but the sender actually doesn't put S itself into the channel, but first uses a code, and that turns S into C. What the receiver receives is the version of C that might have some bits flipped. So the channel might flip individual bits. It shouldn't be too likely that it happens, but it's a possibility. And then the receiver will also need a box that gets hopefully the same message back. But this is not guaranteed in all cases. So we start with a source message at the sender. We use an encoding to turn this into a coded message, which again is a bit string. That goes through the channel. Some bits might be flipped, and then the receiver tries to decode that coded message back to the original message. And the question will be, how much is it allowable for the channel to mess with the coded text before the decoded original message is no longer the same? To make our life a little simpler, so the setup is fairly general. I didn't say how long these messages are. It turns out that all the codes that are relevant for us are of a specific type. They're so-called block codes, which means they work by dividing the message into, well, dividing the stream into messages of a fixed length, each k bits long. And then we separately send each message encoded as a block. So S and C is still the letters that we will use for this, but we can now restrict our attention to a given fixed length. And it will be up to the code to decide what is a good choice for the length of this message and the length of this block. Makes life a lot easier because we can just look at each block individually. And the question will be, if I send a single block, how much errors, how much modification from the channel can I tolerate so that I can detect these errors or correct them. If I have a block length n, well, the possibilities are I can change none of those bits or all of them or anything in between. And the question is, how many flip bits can I detect? How many flip bits can I correct? That will be the core properties of our codes that we're interested in. And we'll also talk a little bit about how this decoding can look like. But that's the core definition. So let's keep in mind the k and n. That's the length of the message, and that's the length of the block. So usually k is a good bit smaller than n, and obviously n minus k divided by k, that's the redundancy. That is the number I asked you for in that question. That's the extra bits we have to add. N minus k is the extra bits that we add per bit in the original message. That's exactly the number I asked you for. All right. For the lower bounds, it's one important notion is that of the code distance. So that will be a couple of definitions. Maybe before we start with this, I think the whole session today will be relatively lightweight and easy to digest, with maybe the exception of this and the next slide, which are a little more mathematical, but then the rest will be fairly easy going. So collect your energy and focus them on these two slides. Those are the toughest. Once we got through those, the rest will be a good bit easier. First of all, whenever I have a block code, I can say that's just a function that maps any bit string of length k to some bit string of length n. Now these functions had better be injective, which means they don't ever map two different messages to the same block. That would be stupid if they did, because then there's no way we can decode this block into the correct message. There's two possibilities, so the code would be not unique. This statement is just the mathematical fact that we need these encodings to be decodable, same as for compression. Now let's define the set of code words, those that actually correspond to messages without errors. So this notation here should mean the set, so this it's maybe not perfectly standard notation. It's the set of all bit vectors of length n, so that there exists a message of length k, and the encoding of that message is y. That's just the meaning of this notation, putting a set into a function that actually just accepts a single element. It's meant to be the set of all answers that you could possibly get by putting all possible elements into the function. So this is just a set of code words is always a subset. The set of code words is a subset of all possible bit strings of length n. And it will have size exactly 2 to the k, one for each of the possible messages, the bit strings of length k. We'll call these the valid code words. Those are the ones that we expect to see if the channel does not flip any bits. If anything is unclear that I'm saying, please ask a question on Slido. don't forget about that possibility, since it's only the second time we use the tool. I'll probably remind you once or twice. These are the valid code words. We expect a valid code word if the channel did not flip any bit. Then we only expect these code words that are in this set curly C. Those are the ones that are perfectly decodable. Now, if we find something else, if we find a block that is not a code word, then the best thing we can do is find the closest valid code word to it. So the one that requires the least bits to be changed. And that is the one with minimal Hamming distance. This is a term that we've used before. So decoding is, well, I can be very formal about this if you want. If we receive a block C, which is not in the curly C, so this is a normal C, which denotes the block that we receive. Oops, now it's gone. This is the curly C, the set of all code words. And if this is not one of those, we know some error has occurred. And moreover, we can decode C2. Well, the message where the Hamming distance between what we should have seen for that message and what we actually received is minimal. So argmin is just a way of saying the result of this whole expression should be the value m for which this was minimal. So we're trying to find the message, we're trying to decode this invalid code word to the message whose correct code word is closest to the one that we received. That's a fancy way of saying find the closest valid code word and decode as if you would have received that code word. All right, just to sprinkle in some more math. The distance of codes of a given code, we call the distance of that code the smallest Hamming distance between any two code words. So you take any two code words in this set curly C, and then their Hamming distance. How many bits do you have to change to get from one code word to another valid code word? That's a quantity of core interest for any given code. Why is that so? This distance has implications for the error detecting and correcting properties of that code. And we have to read this very precisely. So if you want to detect d-1 flipped bits so that you can still see, you can still say definitely something went wrong in the transmission. That's how detection works. It's only a yes/no. Something went wrong or all is fine. If you want to detect d-1 bits, then you need a code with code distance at least d. Because, well, suppose our code had just a smaller distance, then it's possible to flip d-1 bits and go from one code word to another valid code word. But if we receive a valid code word, we take it as this valid code word. So there's no way for us to recognize that there has been an error in the transmission. So we definitely need d-1 bits. We definitely need distance d to detect up to d-1 flip bits. The second part is if we want to correct bits, bit errors up to, well, this quantity. Let's call this t. And you can reverse this to get the d that you need. If you want to correct a single bit error, then you have to make this quantity t, so you need at least distance 3. If you put in 3, then this is the first time at least 1. Right, so this is a little more subtle, but here the point is, if you have a valid code word here, so this is code word 1, this is code word 2, both of these are valid, and now suppose you receive something. This is the code, the block that you actually receive. You have to round it to the closest code word. Well, if these are both within distance t, then you don't know which one is the correct one. Then it's not unique. So you need at least one of them to be at distance strictly more than t to decode that message. So say if that is at least t plus 1, and this is at most t, you would decode this as if you had received C1 originally. But what does that mean for the distance between those two? The total distance between those is then 2t plus 1 if you max this out to have the largest distance. And that's effectively the d that you get. And there's well, you have to be a little careful with d being even or odd. But basically only odd distances are really useful here. Okay, so to wrap that up again, if you're given a code, you can compute the set of code words, and you can compute this distance of the code, which is just the smallest distance between any two code words that are valid. And given this distance, you can already say that this code will never be able to detect more than d-1 bit errors, and it will never be able to correct more than d-1 half rounded down bit errors. And that's just from this simple observation. Now we can actually strengthen this a little bit, and that's another main advantage of this mathematical modeling that we've done up to now. There's two bounds that I want to present to you. So specifically, I mean, okay, let's go back a second. So this is nice. If you know what the distance of your code is, you can say it can't do better than these two things. Now, for our block codes, we have to somehow choose a lot of things. We have to choose the size of the message k. We have to choose the length of the block n, and we have to choose how we map messages to blocks. There's a lot of flexibility, and the next slide gives you some lower bounds, which means impossibility results. You can't do better than that with a given choice of parameters. So this is what this is about. It's trying to make a little more concrete predictions, what you could choose for parameters as just looking at the code distance. So the first of these is called the singleton bound, well, after a person called Singleton. And it says that 2 to the k, which is the number of code words, it has to be at most 2 to the n minus d minus 1. So if you're given the distance and the length of the codes and the length of the message, you can figure out how those relate to each other. And Singleton proved that this is always the case. And you can rewrite this equation as you have to choose your block length to at least k plus d minus 1. All right. So this is to say, if you want to create a code with distance d, which again you will need if you want to detect d minus 1 bits and d minus 1 half rounded down correct, or want to correct d minus 1 half rounded down flip bits, you have to choose your block length at least as k plus d minus 1. There's no guarantee that you can easily find a code with that length. It's just a lower bound. It means the block length has to be at least that. The argument behind this bound is actually not very hard. The idea, so this is just for fun if you want. So this will not be part of the official content of the module, but I think it's an easy enough proof to briefly discuss it. And if you don't follow that part, it's not so important. The argument is if you have 2 to the k code words with distance d, that's the assumption. And now let's try to prove something about their length, about their number of bits. Suppose you delete the first d minus 1 bits of each code word. So here are your code words. You write down all your code words. That's curly C, and they have distance d. Now you take the first d minus 1 bits and you just remove them. What's left is another set of code words, d minus 1 bits shorter each, but they are still all distinct. They still all have Hamming distance at least 1. Because the original ones had d and we deleted d minus 1 bits, there must be 1 bit different left between each pair of these. So these ones still have Hamming distance at least 1 between each pair. Let me remove that part. So if there's so many and they're all distinct, then they must be at least, their number is still 2 to the k. But the shorter substrings, there's only n minus d minus 1 bits left. So we can only have 2 to the n minus d minus 1 different such strings. That's why the number of different strings can be at most that. That's the number of bit strings that are left. Okay, so that's the first bound. Singleton bound is fairly simple, but it's often not strong and not achievable. It's a little weaker than you would like it to be, and that's because it's a fairly simple argument. A second lower bound that Hamming himself proved says that the number of code words is less than this quantity, which looks a little weird. So it's also not so nice to invert it and say what n has to satisfy. But if you're given values of n, k, and d, you can check whether this inequality is satisfied. And his idea was to essentially start from this decodability of the error correcting idea. If you want a code that has distance d, then if you take your code words and you put a ball around each, I will come back to what a ball means in this sense. But suppose you're just in 2D and all those points should have distance d, then t, which is essentially d divided by 2, but with a minus 1, so that it's strictly smaller. If you put a ball of radius t around each of these code words, then those balls are not allowed to intersect. If they were to intersect, then that would prove, like here, that would mean that these 2 points actually have a shorter distance. They're not distance d apart. So this cannot happen. The balls cannot intersect. So what is a ball in the sense of bit strings? Well, let's just do a simple example. If t is 1, and we start with a bit string, just some random bit string, the ball around this would be flipping each possible bit. So I could flip the first one and keep all others intact, or I could flip the second one. Let's put that down here. So, or I could flip the third one. I don't know, put that here, and so on. So for each position that I can flip, there would be an entry in this ball around this center point. Okay, I hope this is it won't really look like a ball. It's a high-dimensional thing and it's discrete, so it's a little nasty. But it turns out you can count how big these balls are. That's essentially these binomial coefficients. If you're not very familiar with those, don't worry about it. The idea is that you just count how big these balls are, and then for each code word, multiply it with the size of this ball. And that has to fit inside your space of all possible block strings, of all possible n-bit strings. Otherwise, there have to be overlaps, which would then kill your distance. Okay, so that was a wake sketch for each of these 2 lower bounds. And what we can do, what you can do is, whenever you find a code that you feel is good, you can insert n, k, and d into these bounds and see how close it is to that. Or the other way around, if you feel you'd like to encode a certain message length with a certain block length, and you know how many bits you would like to correct, so that gives you your d, then you can insert into this bound and see if it's at all possible. And if that inequality is violated, you know such a code cannot possibly exist.